So that's why we finish that with torque equation that's important, which is constant multiplied by IA, and then the power output mainly about the mechanical power. So mechanical power will be torque multiplied by the omega, which is the speed. So that's the two basic equations, we're able to get that done. So that's a really fundamental method. We look into the motor system. So next question about the back EMF and also the armature resistance. So in here, we got DC motor, which also has a torque constant. You see this torque constant is called, the unit is voltage divided by radian per second. So, but that unit mainly come from the back EMF. The back EMF constant is the same as the torque constant. The torque constant, the unit is Newton meter per M, right? But they're the same. I think all the study with consider the back EMF constant the same as the torque constant anyway. But if you present them, you need to present a different unit. One will be using voltage per radian second, or the other one using Newton meter per M. So now then for this one, we have supply voltage 120, armature resistance 1.5. So we calculate load speed. When a motor without any load, what's that mean? A motor without any load. Without any load, that means the torque equal to 0, right? Without load. Torque is the output torque that is to control the output mechanical system. So without any loading, that means the motor is free running. Although the motor has slightly different small bit of the friction, but usually we don't think that would be important, right? So we just, for calculation point of view, we consider them as 0. Just like in power converter, without any output, then output resistance equal to infinity, right? In here, we assume the IA equal to 0. So that means when with no load, then IA is 0 because torque are proportional to current. So do remember that. And then in this case, if IA is 0, then the voltage equation, we have voltage equation equal to EA plus IA RA, right? So now this equals 0. So these two are more like equal, right? So that's the way we can estimate. So all of DC motor as well. Then if without any load connection, if the motor is free running, then we can able to use this method to input voltage that would back EMF. So now then we have these two are equal to each other. Then so that means input voltage will equal to back EMF, which is equal to a constant multiplied by omega. So now then you measure the omega, measure the speed, you measure the input voltage. You can therefore get the back EMF constant. So that's one way we can able to study a motor. If you ask you, I give you with a pure DC motor, can you therefore estimate the torque constant or the back EMF constant? Yeah. So that's the one to do that. Sheldon, did you implement that in your lab? How to estimate the torque constant using this method?
Yeah.
Okay.
Use a speed measurement in the get the voltage current IA reading to get the back EMF in the EMF constant and torque constant.
So later on we have look how you set up the lab and then we discuss after the class. So that's one of the way we can measure the torque constant. And then next thing is to, so the load speed now equal to 120 divided by the parameter. And if that is constantly given, then that one will give us the load speed. Yeah. So another way will be, if you want to calculate any motor without any loading, what the speed is, then that's the way to calculate it. So 600 radian per second. So we usually convert them in RPM. So that's a more popular presentation. So for the load condition, when the motor now join certain current, if the motor join 10 amp, that means there must be some load connected to the shaft of the motor. So what's the new speed now? So 10 amp. So now then, So we go back to the voltage equation. The input voltage is minus voltage drop on the resistor. So that means 120 volt minus 10 amp. Just now we say 10 amp here. Then we can therefore get the 10 amp voltage drop on the resistor 1.5. Then we get the back EMF. So now once we get the back EMF, then we can use the back EMF equation to calculate the speed, rotational speed. So you get back EMF divided by the torque constant, which we know it, then we can have that things. So now then 525 equal to 5,000 RPM. You can see that without any load, the speed would be, of course, would be fast, the top speed. And then in here, the speed will be equal to 5013, slightly drop because of the voltage drop in the resistor. So the output torque now, we got torque constant multiplied by 10 equal to 2 Newton meter. So that means under that load condition, the output torque equal to 2 Newton meter. So fair enough, that's how we make use of the equation to calculate the motor condition. Yeah. So there's this, you can see that it's a very basic equation we have been using. So next thing is to talk about how to examine about the motor constant, like the torque constant or the back EMF constant. So using the nameplate data for the motor, all the motor, unless it's really toy motor, but reasonable large size motor, they have the label called the nameplate. That nameplate will tell you what the motor is, like the power, the voltage, and the RPM. They may not tell you the RA because the user don't need to know the RA. But here, this question, if the nameplate is this one, and the full load current, 7.2 amp, full load current, and the armature resistance usually will be constant, independent of the current. So calculate back EMF. So again, we can do that. The input voltage is 240. So that 240 is the one applied for the whole motor. When you apply to it, then of course inside the motor we got RA resistance. So that means the 240 volt, after we take away from the voltage drop on the armature resistance, 7.2 amp multiplied by 2 ohm, that will give a 225 volt. So this voltage will be appear on the back EMF. So now then, once we got this one, we can able to relate them into the back EMF equation. So now then you say, the nameplate is say 175. Let's see 1750 we convert into SI unit radian per second first. And then when we 225 volt from here, and then divide by 183 will give you 1.23. So that will give you the data for the back EMF constant. So that mainly come from the nameplate. The nameplate will give you the rated speed here, and the rated voltage here, the rated current, then it will give you the rated speed, the torque constant or the back EMF constant. So that's the way you can use the nameplate to estimate about the motor constant. So if the first question asks us, we get the back EMF constant, how about the torque constant? So in theory, I assume them to be the same. We just divide them 1.2 into here. But the difference is mainly the unit. If I ask you about the torque constant, the unit will be Newton per amp. If I ask you about the back EMF constant, it will be voltage per radian per second. So that's the way to do it. So all the three examples are quite straightforward. Just make use of the torque constant, back EMF constant, and also voltage equation. The first question is the power and the efficiency. So the question here is, we have motor 1750 RPM, but we continue with previous parameter from this tutorial. So from previous tutorial, we know the motor 1.5 kW, 240 volt, RA2 ohm, and the current 7.2 amp at the full load. Now we calculate power, calculate output power, right? So the input power, input voltage 240 multiplied by current, the motor current. Because now then we assume the motor under DC 240 volt, we are not putting any PWM there. So that means input power 1728. So here, from here, you can know that input power. So 1.5 kW more look like the output power rating. Yeah, but this will be input power with consideration of the power losses. So let's see the output power to see if that really the case. So we now have the torque constant because previously you calculated torque constant and then we multiply by the rated current 7.2 M, then give you the Newton. And then the speed 183 from previous here, 183 here. The motor is rated 1750, so the rated speed will be 183 radian per second. We use that rated speed and then put into this equation and get the output power. So the rated output power is 1624. So this tool will give you the input and output power. So you see the output mechanical power, you can also divide them from the back EMF because the back EMF we sell are mainly connected to output. So the back EMF voltage 225 multiplied by the current will also give you the back EMF power. So these two should be the same because we know that the torque constant and the back EMF constant are the same. So the efficiency now is the output divided by input. So that is, so we can see that 1624 divided by 1728 will give you the efficiency 93.9%. So that's a very common way we can examine about the motor condition, right? So you can see that all the previous 3 to 4 tutorials are only based on the voltage equation, torque equation, and also back EMF equation. So they are all simple. But I think you had done that in a few years' time, a few years ago, right? Now I have give you a refresh your mind. Make sure you can reuse the equation. But last tutorial called the series motor. So the series motor is slightly different from the previous four. Previous four are talking about separately excited. So the magnetic field are separately connected with a voltage source or PM. But in here, the magnetic field coil are connected in series with the motor armature. So that's so-called the series connected motor, right? So because they series connected, so the armature resistance and the field winding resistance, you can add them together because they pass through the same current. So that would be call them 0.5 ohm. So now then the torque equation, we are provided to you torque equals 0.05 multiplied by IA squared. Before the torque is only proportional to IA, but now IA squared. Why is that? Why this motor different from other motor?
No, we have in series, we have two.
Yeah, exactly. Because the field winding is same as the IA armature current. So that means the field winding are providing you the magnetic flux. So the torque here usually proportional magnetic flux, proportional IA, but magnetic flux are also proportional to IA anyway, so become IA squared. So that's why for series motor, then we provide IA squared. So now this is the equation. They have a new constant 0.05 multiplied by IA squared. So now if current is 220 M, that's the torque. So for the back EMF, now you can see the whole input equation become this. Input equal to back EMF plus current drop on the 2 resistor. So that means V minus the, so I have a typo here, that should be subscript, right? So that total together is 0.5 anyway. So 20 M multiplied by 0.5 will be the voltage drop equal to 10 volt. So the actual voltage for the back EMF equal to 90 volt. So that's all. So the torque is 20 Newton meter. The back EMF is 90 volt. So this don't have any complication, just to show you how the two resistors connect in series, to show you a basic operation for series motor. Any question? Have you done that in the past? I think you are really much familiar with that kind of the problem. Right? So that gives you 5 sample questions. How the, yes?
Which motor windings connected by parallel?
Yes, we had the shunt winding, shunt motor, but I did not have a tutorial here. This, I show you the series. You see when you using the shunt motor, then the armature voltage still the same. Apply the total V voltage to the whole armature. The armature consists of RA with back EMF. And then this whole voltage also equal to the field winding voltage. So that means that can be there. But in this case, the torque may not proportion to IA squared because they are not seriously connected. The special observation here will be IA squared. That's this. But if shunt motor, it only proportional IA. And also the torque constant can be different now because if a shunt motor, we independently control the magnetic flux to the motor. So the torque constant will not just equal to constant, may be controllable. Now in the previous equation, you can see the torque are proportional to the torque constant plus the phi. If the phi is separate excited motor using shunt, then this phi also controlled by the shunt resistor and the input voltage. So anyway, so that's a typical example you can see for DC motor tutorial. Any question? Do you feel it's too boring? Too simple? To refresh your mind, yeah. You did that in the past, probably 10 years ago, but now refresh your mind. Make sure you do remember that. Okay, next thing to do will be so in the tutorial, we like to go for another 5 tutorial related to the PWM control of DC motor. So this PWM control DC motor are mainly based on we have positive modulated square wave applied to the motor system. And then you can see how the equation look like. So bear in mind, this is only a simplified format for DC motion control. For the real case, we don't have to use this method. This method only valid for certain conditions. But in here, just show you one of the scenario, how we control them by a simple chopper. So that means different professors have different presentation, but I use this presentation to show you how the motor works under that particular condition. But for more complicated control, we may need to control differently. So anyway, we have DC motor are controlled by PWM converter with 200 volt DC. So now 200 volt DC source. We're not applying 200 volt to the motor, but we through a PWM converter to do that. The switching frequency of 10K, armature resistance 0.8. So we now say if the duty ratio for the PWM converter is 40%, calculate average voltage appear on the armature input. So that means we have DC source for a chopper to the motor. So that 200 volt is not go to the motor for the chopper. So that means to get that, straightforward, we're just using average. So that is to say the input voltage, the armature will be the VDC source multiplied by duty ratio 40%.
This is the voltage across chopper.
Yeah, there's a simple chopper. Yeah, PWM converter. It's a really the one we show you the DC chopper. Yeah, the most simple DC chopper. So that means 40% multiplied by 200 volt being 80 volts. The average voltage we apply to the armature will be 80 volt. So this is same as our previous notes when we talk about the PWM chopper applied to a DC motor. So B, if the motor is stationary, that means it's not moving. So not moving, that means omega must be equal to 0. Then the back EMF is also equal to 0 too. So calculate average armature current when the duty ratio is 40%. So now then the motor is just stationary, not rotating, EA equal to 0. Then we just have a simple resistor in the circuitry. The total input voltage will now need to apply to the motor resistor. So that's why you look like when we start up standstill, because we have no back EMF, total 200 volt, although it's 50% duty ratio, 40% duty ratio, this total voltage will apply to the resistor and it give you that's a maximum current. You can see from the armature standstill circuitry. Then because internally you got an inductor, so this current will be holding there. And then we may have a feedback loop in order to continuously have this high current for a short period of time during the startup. So that is to say, you can see that here, the average voltage, 80 volt, but the average current, not average current, the IA current, armature current, is 250 amp during the startup. So bear in mind that startup current usually will be large because the back EMF equals 0. We don't have any opposite voltage to reduce the input voltage from the DC source. So all the current just look like a short circuit condition. So the whole current will go to the DC motor. So this kind of the duration, we don't like it to be too long. So if you're holding the motor, don't allow the motor to rotate, the motor will get very hot because we got huge current to go to the RA. Armature resistance will heat up the motor. So this kind of the, like when a motor is stall that means suddenly stop, then that means we don't have back EMF. So if the motor don't rotate, we have problem. The motor will have really hot. So that's the thing we don't quite like. From this equation, you can see that the motor current can be really large. If you calculate losses, 250 amps square multiplied by R, then that will be really high power losses. So that cannot be for a long time. So we should allow the motor continue to go up the speed, then the back EMF will come into, and then you can opposite the input voltage. So next question is to calculate the speed and torque under PWM control. So we have separate excited DC motor, have this parameter RA and also back EMF constant. So you see back EMF constant with voltage per unit radian per second. So it also controlled by PWM with 300 volt DC source and 70% duty ratio. So the armature current is measured to be 50 amp. Now we calculate back EMF. So the back EMF, we got 300 volt DC here, and duty ratio 0.7. So the average voltage appear on the armature voltage would be 210. So now then, we're using this voltage equation. So 210 average voltage minus the volt drop on the resistor, then will give us 205 volt. Yeah. So next thing to do, we calculate the motor speed. Motor speed in here, we got 205 in the back EMF. So that back EMF will be much lower. Because you can see that usually back EMF will be really close to the DC source voltage. But now we got chopper. We already reduced the voltage from 300 volt to 210. So 210 should be really close to the back EMF voltage. So yes, bear in mind, 300 is really large compared to 205. But now we only at 210. So this 205 voltage will be used to calculate about the speed. Now we have the back EMF constant 0.25. We can get the rotational speed for the motor under that condition. So again, we convert 820 to RPM. So that's how we calculate the motor operation in radian per second. So the last bit will be the torque, how much torque being developed. So again, we use the same torque constant and multiply by current 50 amp here. So we control 0.5 Newton meter. So the whole tutorial here, we are using a chopper can reduce 300 volt to 210 volt. Once the voltage being reduced, then the back EMF voltage also become reduced. Then so we got low voltage, then we have lower speed. So we can actually to use duty ratio to control motor speed because the input voltage can vary, we can therefore vary the EA. So this input voltage from a DC source or DC power supply through a duty ratio, we can have low voltage. When we have low voltage, then we had lower back EMF voltage. Because we are now doing motoring, the motor back EMF voltage must be less than the input voltage. So now that's why how we can get to this calculation. Very simple, straightforward. Same as previously, but we just adding a chopper to reduce the voltage. That's all. We don't have any complication here. So let's to look into the dynamic braking. So for the braking, then let's see how it look like. A DC motor with armature resistance 0.5. And then we are now dynamic braking. That means we remove the DC source, putting a resistor there for the dynamic braking. So during this, when this motor is running, and then the back EMF equal to 100 volt. If suddenly we disconnect power and connect across the braking resistor, that's what we say. We don't connect power source, but connect resistor to break the motor. So this method called dynamic braking, and calculate initial braking current at the moment when we turn off, and also calculate the torque, the braking torque if the motor constant 0.8. So let's see how we do that. So the initial braking current. So during the dynamic braking, the motor will be generated because back EMF is just like voltage source, still rotating this voltage source. So that voltage source will go to the braking resistor and produce some braking current. So, but this voltage have to pass through two resistors. One is the braking resistor and also armature resistance. So the EA will become a source to generate two kinds of the power to RA and RB. So that means if you want to calculate braking current, then you have the back EMF divided by summation of two resistors. So that means now you see the question here is 100 volt. 100 volt divided by the two resistors, we got 40 amp. So the braking current will be 40 amp. So the initial braking torque. So you see now the current is not going inside the back EMF, but going outside the back EMF. So that's why in operation we consider them as negative. Positive means go inside the motor back EMF. Negative means going out. So the torque here will be, you see the torque constant is unchanged even though we are changing from different mode of operation. Torque constant more look like a physical parameter inside the motor. So this multiply the braking resistor, which will be this one. So you can see from this problem, the braking torque amount will break the motor depend on the current, right? IB current. This parameter is constant. We can't do anything to the braking. But IB is the control parameter, how good we are now braking the motor. So if you want to change the IB, one thing we can do with the IB equation is controlled by the RA, which is fixed. But this second IB, second RB, you can change it. So that is to say, I think I also asked you before, what kind of braking resistor is the best? How is it large RB or small RB to brake the vehicle or brake the motor? Yeah, I think Ali answered me this question. Yeah, I think last week or the week before, what's the best RB? Small one. When we have small one, we can join large current. We try to extract more current from the back EMF so that you can take out its energy. So that's why I tend to use small. So next question is dynamic current ripple. So we in DC pure DC motor, we does not consider the ripple in the armature. We just purely DC, but in all the actual scenario, there must be ripple because we are now using PWM to control it. If we're only using pure DC voltage, we don't have that. But today, all the motor control, we need to control the motor torque and motor speed. So that's why they're all controllable. So for this question, we have PWM driver with 120 volt DC. and switch at 20K, and motor armature resistance 2 milliamp, and the current 50 amp. Now they just ignore the resistance for the calculation. That make the PWM calculation much easier. So the first question will be, if you transfer on for 30 microseconds, what's the duty ratio? So T on will be 30, and then the period, we have now 20K. So 1 over period will give you the TS. So plug into here, we can know it's 60%. The duty ratio for this scenario is 60% for the braking. So the current ripple here will be basically from the ripple equation. The ripple equation, we did that in the past, like the delta I, A, U to something, right? If you do remember that, I can show you back again the formulation. The last few slide there. So this is the formula, right? The ripple current. So that basically from the voltage equation, from LDIDT equation. So in voltage minus back EMF minus the work done on the resistor and divided by LA will give you the ripple current. So we are now looking into delta I. Delta I mainly come from this, the basic LDIDT equation. And then delta I is equal to the voltage on the inductor multiplied by delta T divided by LA. So the voltage actually come from the previous looks there. So now then we have, go back to here. We got 120 volts. So this voltage will apply to the inductor anyway, the whole inductor for the motor. And then we divide by the time, because the turn on will be 30 microseconds. Within 30 microseconds of time, the voltage applied to the motor and the motor winding will have current will go up. So we call it delta I. So that is to say, you can see the ripple, 1.8 ampere. So the inductor current, once at 120 applied to them, it will go up to 1.8. So the peak to peak ripple voltage is equal to this 1.8 amp. So you can see it in here, and the ripple is 1.8 amp. So that means what's the normal current? The more normal current is 15 amp. So 15 amp, we got about 1.8 is the ripple. So that means the top will be 15 amp plus 1.8 is the top one. The bottom one will be minus. So there's a up and down. We call the middle with the average. We have this top part and bottom part. So that is to say, we usually assume the current will be straight line here and then up down. And then this amount is our peak to peak, so-called delta IL, right? That's how we get that. Anyway, so the last one will be the pedal driven motor. So for this motor, again, the input voltage will be 400 volt, usually high voltage. And the armature resistance 0.08, the torque constant is 2.0, armature inductance will be 1.5 millihenry. Again, I mentioned to you, Henry is a really large unit, so we usually use millihenry for all this motor. Duty ratio 50%, calculate armature current. So the voltage applied to the armature, again, we use duty ratio, right? The voltage is average voltage. 400 volt multiplied by 0.5 becomes 200 volt. That's average voltage. You can see from the armature. And then for the EA armature voltage, taking out the volt drop on the resistor, then we give you the 192 volt. So that's reasonable because we got 200 volt only applied to the motor. And once we got the back EMF, we can divide by the motor constant. We can get the radian per second of the motor speed. Under the condition of the operation, we got 96 radian per second. We change them in RPM, easier to observe. So the torque we are having, then we got the armature torque constant, 2 multiplied by 100 M, then we give you 200 Newton meter. So that basically will be how we calculate using back EMF equation and torque equation to calculate the torque. So this tutorial is not very complicated, very simple tutorial, which are really much similar to what we have been doing in the lecture. So over here, you can see that we need to use chopper Peter M to reduce the voltage. So the motor armature will see less voltage using the duty ratio. And then the inductive current for the motor, because they got big inductor there, we cannot assume the inductor equal to 0. We still have some energy holding there. So this current will continue to flow. When you turn on, this current flow through the input. When you turn off, the current looping in the diode loop. So that's why you can see that. Let's go back to the lecture notes we have the other day. So last week we were just doing that tutorial, just finish it. So you see, for this tutorial, we also have high voltage in here, but after DC chopper, this voltage will be lower using the duty ratio. Multiply the input, multiply the duty ratio here, we got this voltage. So this voltage across the armature will be lower voltage. And then the back EMF will be have a large percentage from this average voltage. But when we turn on, the whole DC voltage is assigned for the whole thing, and then we have current pass through the IA here. So this current, after we turn off this current, we need to looping in this loop. So that's why I can see that. So when conduct, the current will going through here in this loop. And then when we turn off, this current should be looping around the smaller loop here to continue with the current. So you can see that here, this current will, let me get my pen. Where's the pen? I can't draw it. So this current, what waveform is it? When you turn on, the waveform will be more like square wave, right? This current, the IDC current, will be look like this. And then IA current, because there's a motor inductor, so the current for here will be more constant without any effect. So this IDC. This is how the current look like when we do the switching. And this voltage, VD, the voltage across the dial, it also equal to the voltage across the V in. What's the voltage waveform? Of course, also, when you turn on the whole voltage apply across here. Yeah. And so there's a VDC. And when we turn off, then the dial will conducting become 0, right? So the waveform will become this. This is how the waveform of this shall look like. So this waveform is this one. This is the waveform for the motor voltage. I think you all understood. Right? Then we also have this dial current here. What's dial current waveform look like? When we turn on, so this is on, this will be off. Right? When you turn on, all the current go through here. No current pass through the dial, so that means initially the dial current equal to 0. But next, when you turn off, the current will be looping. So that means the dial current will behave as such. So this level will be equal to this level for the armature current. So that give us all the basic waveform around here, the voltage and current waveform for the chopping DC motor system, right? Let's summarize what we have learned. But anyway, so how to erase it? So to summarize what we have learned for this lecture will be, when a DC motor usually will be controlled by a power E circuitry, and then PWM shall be used. So in here we show you a simple duty ratio to control the voltage. And the current for the armature will go up and down because there's inductor there. Without inductor consideration, if the inductor really, really small, we don't consider that. Once there's inductor, we can know the current going a triangular waveform look like. The ripple for the current are controlled by the turn on, turn off time. And the torque is also controlled by the ripple current. So we usually assume for motor design, the ripple torque will be less than 5%. That's the best. If more than 5%, you may feel there's some vibration for the motor shaft. So if you want to reduce the torque ripple, what you need to do will be you have to use higher